Okay, I'm going to retry this last example one more time. So step number one, we're going to say debug step into, which brings us to the first instruction, but I'm going to scroll down to our test for table initialization using obviously using our index scaling right here. And so this is the instruction where I would like to say set next statement, and of course IP gets updated. Now I would like to display the address of my table one more time. So this is the address of my table. Switch to memory view. So it's being all zeros, and now I'm just going to point to the return instruction after the loop and say run to cursor. Okay, and you can see that all 100 of these 2 byte size integers were updated to 5. Okay, so this is a demonstration of the work, this scale index indirect memory addressing example. And on this slide, you can see that in this graphic right here, the possibilities are that if you want to combine all of the indirect memory addressing modes that we discussed earlier in this section, you can combine the base register with index register multiplied by scaling factor, and scaling factors are 1, 2, and 4 and 8. So these are 4 different scaling factors. Of course, 8 is for 64-bit values, and 4 is for 32-bit values, and 2 is for 16-bit values, just like we had in our example right here. This is scaling for 16-bit type of integer, so that's our case right here. The great thing about this is there is no performance penalty for using a scaling factor. This is why when we use arrays and we need to apply scaling with respect to memory allocation by each element of the array, this is much more preferred way of doing things rather than figuring out how to update the index manually by adding the correct offset from here to here, from here to the next one, because we definitely need to know what type of increment to apply to index into our array. So, but these are all possible combinations. So index register, base register, so the base can be any general purpose register. Index can also be any general purpose register, like EAX, EBX, and so forth. Then the scaling can be 1, 2, 4, or 8. And you can also combine it with displacement. Okay, so displacement, it can be any 32-bit type constant. And so what happens is that in the end, of course, it's just another reminder that the final result is that this value in the register scaled, which is simply multiplied by one of these values, then combined with displacement produced by the table, which is actually displacement of this table inside of our data segment, which is a relocatable segment, right? Altogether, all of this combined results in an effective address. And so this whole idea is that this is how our effective address is calculated. Internally, everything starts with the segment register. Then we use the base register, which is optional. You don't have to have a base register. The base register means that we could combine EDI times 2 with another register, like EAX plus EDI times 2. And then we can use the index into array, specifying array element. Index is 0, 1, 2, 3, 4, 5. Pretty straightforward approach here. That's the whole idea of scaling. Then the scaling factor, and then finally also displacement, which is just a constant value. And so this is how it's all being gets computed, and you get the effective address as a result of this type of approach to use scaling. So these are more examples of using scaling, different syntax for scaling, and this is just something definitely that we absolutely need when trying to access individual elements of arrays when coding in assembly. So I'm just going to stop my debugging session. And so this is a series of various types of direct and indirect memory addressing modes, including now our conversation about the scaling factor applied to the array of 16-bit integers.